Hey there, it's me, Miss B, and in this video we are looking at the Unit 4 Lesson 12 Cumulative Practice Problems for Illustrative Math Algebra 1. So we're going to start here with this question about a parking garage. So a parking garage charges $5 for the first hour, $10 for up to 2 hours, and $12 for the entire day. So we want to let G be the dollar cost of parking for T number of hours. Okay, so we're going to do four things then. We're going to complete this table, sketch a graph. We're then going to decide, is it a function? Is G a function of T? And then is T a function of G? So those are our steps here. So first, let's complete the table. Let's fill in our numbers here. So at 0 hours, if you don't park there, you don't owe them any money. So 0 hours, $0. If it charges $5 for the first hour, that means even if you park there for half an hour, it's going to cost you $5 all the way up until the first hour. It's $10 for up to 2 hours, so it'll be $10 for any amount between 1 and 2. And then $12 for the whole day. So that means $12 for anything after that up to like 24. So that's our table. Now we want to sketch this graph for the time between 0 to 12 hours. And you'll notice my table doesn't go up to 12 hours though. So let's start with 0, 0. I'm going to place that on my graph right here. Oops. Here on my tablet, but it scrolled everything with it. Okay, so now we have 1/2 at 5. Basically, up until 1 hour, it's going to be $5. So at 1 hour, we want it to be 5. But it's also for everything up until then, except for not right at 0. So we want to make this a line here and a dot, but have an open circle above 0, because if you park for no time, you pay no money. And all of our graph pieces are going to kind of look like this. So our next step, so to speak, is $10, and that is for up to 2 hours. So 2 is going to be right here, and that's our end point, which means anything exactly at 1 hour and beyond, up until 2 hours, is going to be this little step right here. And beyond 2 hours, it's just for the whole rest of the day for our price. So we're going to start then at $12. So we'll put a circle here that's open, but this line is going to come all the way over for the rest of the day. So that is what our graph actually looks like. It's a little funky looking, but this is a piecewise function. So now let's actually explain, is G a function of T? So G was the dollar cost, so is dollars the function of time? Is G a function of T? That means dollars time. And that would be our standard format. So where G is the output and T is the input, because we would always say output is a function of the input. And in that case, yes, because you would only have one price for no matter what time you parked, you would pay one amount. They wouldn't be charging you two different amounts. So we would say yes. You, we'd say there is we would normally say one output for every input, one price for each specific, well, we don't need to say each specific. We can say one output for each input. Which is price. Now, if we looked at it in the other way and we said, is time a function of dollars? That would be asking, if you told me how much you paid, that I could tell you exactly how long you parked there. And that is not going to be true, because if you told me that you paid $12, you could have parked there for so many different time periods. It would just be obviously more than two, but it could be any amount in here. It could be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to, I don't know, maybe even 24 if that's what they go for. So yeah, is it a function? No. So how can we explain that? We can say there are multiple possible, so there are multiple parking times for each cost. So there's multiple parking times for each cost except for zero, because zero has to be zero. But for the rest of them, there are multiples. Like you could park an infinitesimally small difference in amount of time, and it would still output 5, whether you parked there for 2 seconds or 3 seconds or 5 minutes, you would still get that charge. So yeah, let's keep going. Looking at number 2, they want to know, is this a graph of a function, and explain your reasoning. So first of all, the answer to that is no. And the reason for that is this. Both of those points I just circled are closed circles, meaning they have defined values at that point. In the previous question, I used what we call open circles or unfilled circles as points. And that implies that one of them can get infinitely close. So we have multiple outputs when the input is 2. And likewise, we also have multiple outputs when the input is 6. So we can say no, there multiple outputs when the input is 2. There are also multiple outputs when the input is 6. Okay. So just recognizing that that solid dot means you are saying that it is able to be equal to that thing. So they're telling us that here 2 is equal to 1, and it's also equal to 7. And it can't be true. And still be a function at least. So it could be something, but it's not a function. Okay, let's keep going. So for this next problem, we are using the graph of a function to answer these questions. So the graph we have down here, we want to find what are some of these values. So what are the values of g of 1, g of negative 12, and g of 15? So let's find those. I'm gonna do, maybe I'll do this with highlighter. So g of 1. It looks like that one here is this value, g of 1. So we maybe have, what is this? That's a 4. Then if we have g of negative 12, I'm going to highlight that yellow. Negative 12 is right here, so hard to see. Maybe I'll like circle it or something as well. Right there. Put a little red box around this. So that looks like, since this goes by 4s, this looks like maybe negative 10 in between here. And then g of 15, we'll make this one's blue. So positive 15, we have here. Now, the real question is, since that is an empty circle, is there actually a function value for 15? And there's not, because they're not giving us one labeled on this graph. We can't actually assign it to a value. So we're going to say that this one is undefined. It literally is just not defined by our graph, so we cannot say that there's a value. Okay, for part B, it says, for what x values is g of x equal to negative 6? So we want to find, when is our output value negative 6? So output value negative 6, that looks like right here. So they want to know, when is it negative 6? So we want to cover these x values, but not quite this one, because technically it lands here. So this looks like it goes from negative 8 to negative 1, but not quite negative 1. So when we describe this, we're going to say negative 8 is less than or equal to, because it's allowed to be equal, x, and then is less than negative 1. Because it's not allowed to be equal to negative 1, but anything that's less than that, no matter how minuscule, that's what we're going to be looking at. So then the last part is to fill out our rule, and actually, define our piecewise function here. So each of these lines is giving you an output value and then describing for what inputs that range works. So it's going to be negative 10 for anything negative 15 to negative 10. So that's this group right here. Our next group is negative 8. And just to check, they're saying that's between negative 10 and negative 8. Looks correct to me. So we'll say negative 8. Negative 6, this is from something until negative 1. I think that's, oh, look, the one I just described up here for negative 6. So that means that this goes from negative 8 to negative 1. At negative 1, that's where it jumps. And so at negative 1, we then jump up to this one here on our graph. So this looks like it is at positive 2, since we're counting by 4 here, and that's halfway. So this would be up output value of positive 2. Let me actually make that look more like a 2. Okay. And then we want to know what are the boundaries for when it is equal to 4. So it's equal to 4 right here. So this looks like positive 1 and up to 10, but not equal to 10 because it's an open circle on this one. So that's why we have, yep, not equal to, it's just less than. So less than 10. And then our starting number was 1. So you'll notice here that wherever you almost touch to end, that's generally where you'll start your next segment, is at that number, because we can't have two equal to it. So only one of them gets the less than or equal to sign. And then here, our 10 is reflected down here. And our -8 is also reflected up here. So we have basically wherever we had filled in things here, their limits are kind of set based on the previous step. So we have that little bit of a pattern. And that's it for question 3. So not too bad, but still a little different than what we're used to looking at. So on to question 4. Now this is kind of a review question, one that we've maybe seen before, but asking some different questions about it. So this graph represents Andre and the distance from his bicycle as he walks in the park. So we want to talk about which intervals of time is the value of the function decreasing to start with. So I like to kind of use some highlighters, and I really just want to look for any parts where the function might be going down. And I see decreasing right here. I also see decreasing right here. And then decreasing right here. So decreasing. Now I can kind of help myself by describing these pieces. Okay, so we want to describe basically our input values here. So for me, this was what, 9 and 11 seconds, and then I also had 14.5 and 17, yeah, 15, 16, 17. And then this one was 21 seconds to 27 seconds. Yeah, that's what it looks like. Okay, so we can say, nope, that was between 9 and 11 seconds. And then this was 14.5 to 17 seconds. And 21 through 27 seconds. Okay. Now they want to know for which intervals is it increasing. I'm going to highlight that green. So anytime it looks like we're going uphill, green. And up the hill here, green. You'll notice this section is neither green nor blue. That's because there is no rate of change there. The rate of change is 0, so it's not changing at all, meaning it's not increasing or decreasing. So I only have 2 intervals where this is actually increasing. So this is between, so it's going to be between 0, where we're kind of starting at, and then this goes up until the 9 seconds. So between 0 and 9 seconds. I want my handwriting to be legible. seconds, and it was 17 through 21 seconds. Okay. And now part C is asking us to describe what Andre is doing during the time when the value is increasing. So if the value is increasing, he's increasing the distance from his bike. So he is walking away from his bike. He is walking away from his bicycle. Okay. And that's all we have for question 4. Keep going. We have question 5. The temperature is recorded at several times during the day. Function T gives the temperature in degrees Fahrenheit, and N is the hours since midnight. So we have a graph for that here. Based on the graph, well, actually, first it says describe the overall trend of temperature throughout the day. So we can put a little description here. So it looks like to me, it decreases a little bit until around like 6-ish. I guess when the sun rose, right? It's decreasing here. We have probably like midnight. So temperature is decreasing, sun's gonna rise, temperature goes up probably until around midday-ish. We can look at the actual time, and then decreases again as nighttime comes around. So what is this time? 14, 15, 15, 16, 17, 17, that's what, like 5 p.m.? Yeah, okay. So we can say the temperature decreased between midnight and sunrise. Temp increased from sunrise until around, do we say that was 5 p.m.? Yeah, like it levels off a little bit there, but until around 5 p.m. Then the temp dropped. Or we'll say decrease. This whole we're really trying to use the words increased and decreased. So we'll say then the temp decreased again. Okay, so that's our overall trend. Now let's actually answer this question. Based on the graph, did the temperature change more quickly between 10 a.m. and noon or between 8 p.m. and 10 p.m.? So I'm going to just highlight some chunks of my graph. We'll say between 10 a.m. and noon is going to be green, or between 8 p.m. and 10 p.m. So we have, it looks like 10, 11, 12 right here. So between 10 a.m. and noon, or between 8 p.m. and 10 p.m. So between 8 p.m. and 10 p.m. We're going to make this chunk blue just so that we can look at it. So 15, let's see, okay, so 20 hour 20 should be 8 p.m. So 20, 21, and 22 would be 8 p.m. and 10 p.m. So just based on this, I know my two bottom dots are kind of close to each other, but if you look at just the verticalness of how far they have to go up, like the length of these, the blue one is actually longer. And these both span the same number of hours. And they're not asking us which one's positive versus negative, they're just saying changing more quickly. So it's allowed to be an increase or a decrease. So I'm going to say that it was between 8 p.m. and 10 p.m. And 10 p.m. And then this was it changes by, oh, how many degrees is this going to be? 50, goes up to 6, so that's 10. That looks like 12 or 13 degrees based on 10 degrees on the green span there. It changes by 12 or 13 degrees in, well, not instead, compared to. So we'll say compared to changing 10 degrees. Over the same number of hours. Because 8 to 10 is the same as 10 to noon, so same number of hours. The blue just changes more degrees. Okay, question 6 is asking us to explain why this does not represent a function. So, the reason for that is because at certain inputs, I have multiple outputs. There is something that we call the vertical line test. So I'm just going to draw myself a vertical line here and make the tablet snap it so it's nice and straight. Then I'm going to lasso it up here. And we're just going to, oops. We're just going to accidentally delete part of it, apparently. We're going to get it back here. Now, I am going to click on resize because I do want to just move this around. Okay. So the vertical line test basically means you should be able to take a vertical line and pass it through your graph and have it only touch your graph of your function in one place at a time. If your vertical line touches in two places like this one does, it touches right here and right here, then you know it is not a function. One of the easiest ways I like to do this is using my pencil as the vertical line and just visually dragging it across, or just in my mind's eye, taking a vertical line and trying to pass it over top of my graph. So we can say this, oops, a little too thick for how much I need to write here. So we can say there our multiple outputs. Those are the y values for many of the inputs, and those are the x values. Yeah, just basically it has multiple outputs for one input. And that is going to be the end of our homework questions for this assignment. So that was the lesson 12 cumulative practice problems. That was unit 4, lesson 12 for illustrative math, algebra 1.